which is equal to, now the total load is nothing but one UVL, that is triangular load, then this point load, then this another uniformly varying load. I can take the full UVL, then in that case we have to find out the CG, because the perpendicular distance we have to find out from the CG of the full triangle, and it is right now difficult to find out. So I divide my full triangle in terms of two different triangles, because for this triangle I know the CG. So now first is 1/2 into 20 into 2. This is load multiply by perpendicular distance, that is of 1/3 into 2 plus 2.5. Now this creates an anti-clockwise moment from the section, negative sign. Next 42.5 creates another moment, 42.5 multiplied by 2.5 creates section left clockwise, positive sign. Then another UVL, half into 20 into 2.5 into 2/3 of 2.5. See, I want this distance, and this distance is 2/3 of 2.5, and this creates section left anti-clockwise, negative sign, and this gives me an answer is of 2.56, sorry, it is 1.25 plus sign 1.25 kilonewton into meter. The answers which I achieve over here is 1.25. Means I have to join this point and this point using cubic parabola, because the load which is of acting of UVL nature. But interesting, please refer your shear force diagram which has been taught to you in the previous class. So refer this PPT. See, the point at which the shear force is 0, refer this one, and this distance is 1.71, means at this point, that is 1.71 meter from the A end, I will achieve maximum bending moment. Means I have to plot a bending moment in such a way, please come on the tabletop, 1.71 distance. So this is the distance that is to be called 1.71 meter. So there will be an ordinate which is the higher ordinate than 1.25. So I have to plot, my diagram is like this. I wish now it is clear to you, and this nature is of cubic parabola. Kindly observe why I have taken this kind of curve, because in case of shear force diagram we found that at the distance of 1.7 meter from support A I got the maximum bending moment, and hence I have to plot this ordinate maximum over here. Now my intention is to find out this ordinate, and that ordinate I have to find out by taking a section over here. Please refer my figure. I have to take a section 1.71 meter. So I have to find out this ordinate. Then I have to take all the moments of the forces at this section. The name of the section is of F, and that ordinate we can find out over here. I wish you can do by yourself. Let the answer is for this diagram is of 2.56. So we can achieve the bending moment value up to the point D. Now, let us we go the bending moment at point D just right, because at the point D concentrated moment is acting. Refer, concentrated moment is acting at D. So, bending moment at D is equal to, this is just right, is equal to. Now we have a value of plus 1.25 at D, just left. Now when I will take just right and 1.25 which is of positive sign, means of sagging nature, this value also a clockwise moment section left clockwise, which is also an additive nature, means I have to add plus 30 and I got it 31.25. So here there is a sudden change in the bending moment diagram. I got this one is 31.25 kilo Newton into meter. I wish you have understood this concept very well. The point at which the concentrated moment is acting at that particular point, bending moment changes suddenly, abrupt changes will be there. Now let us find out what will be the bending moment at E. Hence, let us find out the bending moment at E. Bending moment at E is equal to bending moment at E is equal to the first is of this UVL, that is minus sign, half into 20 into 2 into distance. The distance is 1/3 of 2 plus 2.5 plus 1.5. 2.5 plus 1.5 is of 4 value. Another force which is of this point load, that is the reaction itself at A point and which creates a sagging nature. So plus sign 42.5 into once again 2.5 plus 1.5, that is 4. Next load which is of this uniformly varying load, that is of triangular nature and which creates the hogging bending moment, minus sign half into 20 into 2.5 bracket. The interesting point, the CG distance, and the CG distance from this particular point is 2/3 of 2.5 plus 1.5. Then next is this concentrated moment, that is of addition of 30, that is the plus 30. This 20, definitely 20 into 0 because the perpendicular distance is 0, and we got the answer for the same point is 27.5 plus sign. So I got an ordinate of bending moment which is of 27.5 plus sign. Plus sign means above baseline. Now please refer this figure of loading. If I will enlarge this figure, please see over here this particular figure. See, between D and E there is no load. No load, the variation of bending moment diagram which has been joined by inclined straight line. So I have to join by inclined straight line. So between D and E there is no load, we can join by inclined straight line. Now let us go ahead to the point B. Let us found out What is the value at B? Yes, think and give me the answer. What is the value of bending moment at B? Definitely, as it is the end of the support, the answer must be 0. The answer must be 0. You have to check it out by taking different forces from the left side, and answers must be 0. You can check by yourself at your home by yourself. Now between E and B there is no load. The variation or this join this point and this point by, refer this one, by inclined straight line. Refer this one, this is of plus sign because of sagging nature, and this is of opposite negative sign. This is our full bending moment diagram that we can achieve right now with the combinations of load, point load, UVL, then UDL, then this is of 1. In the previous case, if there will be a UDL over here, then this is shown by parabolic nature. If there will be an UVL, cubic parabola, we can achieve. Now please refer this point. What is this point? The point at which bending moment diagram changes from negative to positive or positive to negative, this point is known as point of Contra flexure. Another name is point of inflation, and we can find out this point of inflation by taking a section in this region, by taking a distance x, and we have to set up an equation of bending moment in terms of x, which is equated with 0. So my equation comes in terms of x cube, and we have to solve this equation to find out the x. This point is known as point of Contra flexure. So this kind of problems we have also discussed in the previous lectures. So please solve by yourself to find out this point of Contra flexure. So I wish that this problem you have understood very well. Please see the diagram that we have been obtained right now. Let us go ahead with the next problem. That is the last problem of the series of overhanging beam. Then we go ahead for the further of the relation between the loading, bending moment and shear force. Let us proceed further with the next problem. Refer the problem. Refer the problem. The given beam, obviously, the beam whose one end is projected beyond the support B is known as overhanging beam. This overhanging beam is subjected to a concentrated moment as well as concentrated load. Our intention is to find out the shear force diagram as well as the bending moment diagram. So what will be our first step? The step number 1 is the determination of support reaction by using 3 static equilibrium conditions, and the conditions are sigma h, sigma v and sigma m at any particular point which is equated with 0. So right now let us go ahead for the determination of support reactions. Let us use the first one, sigma h is equal to 0, and you just visualize this particular figure. There is not a single load which is of horizontal nature, and RAH which is equal to 0. The another equilibrium condition sigma V is equal to 0, sum of all the vertical forces acting on the system, which is equal to 0. So here in this particular forces system, there are two external forces which are acting over here. The first is the concentrated moment and another is the concentrated load. As such, sigma V is the summation of vertical forces, so we do not have to take care any kind of the concentrated moment. We have to take a single, that is of 20 kilonewton load over here. So RAV plus RB, which is equal to 20. Why? Because we are assuming that RAV and RB which are acting upward. Hence, we got RAV plus RB is equal to 20 kilonewton. This is a relationship between RAV and RB. To find out the exact value of RAV and RB, we have to take a moment at any particular point, maybe at A or maybe at B. Now, let us we take sigma MA is equal to 0. Sum of all the moment of forces at point A is equated with 0. So we have to take moment of all the forces at point A. The first, that is this load is coming over here, because RAH itself is 0, the moment is 0. But RAV having some value, but we are taking a moment at that particular point, means this load multiplied by the perpendicular distance is 0. So RAV into 0, it is 0. This is the concentrated moment which is acting of a nature of anticlockwise, minus 20. And we do not have to multiply by any kind of perpendicular distance because direct moment which has been given to us. Next, this RB into 4 creates an anticlockwise moment, means minus RB into 4. This 20 creates clockwise moment, so plus 20 into total distances of 2 plus 2 plus 1, that is 5, which is equated with 0. And by solving this equation, we can find out that RB is equal to 22.5 kilonewton, while by replacing the value of RB, we can get the value of RAV, which is of minus 2.5 kilonewton. So refer the previous figure.